Greetings again to all of my stellar AP Chemistry students. Today I'm going to wrap up our conversation on thermodynamics and then we'll transition into our final portion of Unit 9, which is electrochemistry, and then that'll be the end of AP Chemistry. So, yesterday we were talking about this equation right here, which relates Gibbs changes in Gibbs free energy to change in enthalpy and change in entropy for a chemical reaction based on a temperature in kelvins. Something that I should have mentioned to you yesterday, but I'm going to now, is that traditionally Gibbs free energy and enthalpy are measured in kilojoules, and entropy is met well, these are kilojoules per mole, and entropy is measured in joules per mole Kelvin. So if you're going to plug numbers into this equation, you either need to convert your entropy into kilojoules per mole Kelvin by dividing by 1,000, or convert your Gibbs free energy and enthalpy into joules per mole. And when we look at some other equations we're going to get to, you're going to have to convert to joules per mole as well in order to actually solve them. So, a couple of things to point out about this equation and some of its significance. If H is negative and S is positive, then G is always negative. If H is positive and S is negative, then G is always positive. You look at how things plug in, because a negative entropy times your temperature, that's going to be negative. And if you subtract a negative from a positive, you're going to get another positive. Right? Now, where things get interesting is if they're both positive, or if they are both negative. Because if these are both positive, then G is going to be positive at low temperature and negative at high temperature. And this is going to bring us back to the discussion question from yesterday, talking about the melting of ice, because that is something that is an endothermic process. H is positive. It also increases entropy going from a solid to a liquid. And so at low temperatures, G is positive, and so that's not a favorable process. But at higher temperatures, G is negative, and so that becomes favorable. And there would be a specific temperature where this transitions from being unfavorable to favorable. And in the case of melting ice in particular, that temperature would be 0 degrees Celsius or 273 kelvins. That's why water freezes into ice below zero and ice melts above zero. And at zero, it's kind of right there in the middle. It can do either one. Now, that also means if both of these are negative, then you're going to have the opposite case. Then G is going to be negative at low temperatures and is going to be positive at high temperatures. All right, so let's go back and look at a couple more slides as we wrap up our study on this part of thermodynamics, and then we'll get into electrochemistry. So there is a relationship between Gibbs free energy and the equilibrium constant. You remember our big K, the equilibrium constant. And that is that your Gibbs free energy equals negative R, our gas constant of all things, 8.314 joules per mole Kelvin, times the temperature times the natural log of the equilibrium constant. And so what this means is that if delta G is negative, meaning a reaction is favored, then K is greater than 1, meaning that the reaction favors going towards the products. If G is positive, that means the reaction is not thermodynamically favorable. And so the reaction is not going to go in the forward direction. It's actually going to prefer going in the reverse direction. And then if G is 0, then you are at equilibrium, essentially. It's not favorable or unfavorable. So that's a interesting thing that kind of ties thermodynamics in with equilibrium. And then I want to point this out that it is possible to make a reaction that is not thermodynamically favorable actually happen. For instance, it is favorable for a battery or an electrochemical cell to discharge, but you can apply electrical energy and force the reaction to go the opposite way in the unfavorable direction and recharge. Or, for instance, cellular respiration is thermodynamically favorable because, we're all alive right now. But light energy from the sun can actually cause the reverse reaction, photosynthesis, occur by taking external energy and coupling it with a chemical reaction and drive it in the forward direction. Or, for instance, a lot of the processes that happen in your body are not thermodynamically favorable, but by coupling them together with some ATP to ADP transitions, you can actually use that favorable reaction to drive an unfavorable reaction forwards. So I hope that makes sense. I'm going to give you a couple of sample AP questions just to take a look at. And then we're going to transition into electrochemistry and wrap things up for the year. So have a great day.